Alright folks, so I'm making a second video here to kind of finish this problem up. So again, the problem has two parts. The free body Newton's second law type of parts, in which case we defined kind of up and left positive and down and left positive. And we're able to derive the following equations. This one for the normal, and I think we had one where the acceleration ended up equaling g sine theta. Now it's important to note, I know before we had g sine theta for equals a. That's because we've got a pointing down and left. But again, my position variables here, up and right, is positive. So what I'm just doing is basically describing the motion of this particle with a different set of variables. And here's how they're related. Because the s variable is up and has up and right positive, and my acceleration was to the left, they differ by a minus sign. So if this v is the v linked to these variables, basically it's s dot, then the minus sign is because this acceleration is in the opposite direction. So now the next step is recognizing that we've got, okay, a velocity, a time, and a theta. So we need to write the velocity, this term right here, this dv dt, needs to be converted to a derivative with position information in it. So we can do that using the chain rule differentiation. So this dv dt can be written dv ds dt, and then equals minus g sine theta here. And keep taking note that the ds dt is equal to v. So what we can do now is write this v dv equals minus g sine theta. Now the ds, I'm going to do this off to the side here, from the definition of a radian, ds can be written r times d theta. So converting this to an r d theta and moving it over here, here's what we're going to have. So now integration of both sides is going to yield this. V squared over 2 equals, on the right hand side, the g and the r are both constant. The antiderivative of sine theta is minus cosine theta, making this term positive. Right, and then plus a constant. The next step now is to determine the constant. So we can get that from the initial conditions. In this work right here, when theta equals 45 degrees, the velocity needs to be 8 meters per second. So when we put the 8 here, we're going to have, oh, I'm sorry, 2. It's not meter per second, it's feet per second, my bad. Let me go back and change that. I don't think I'm going to redo the whole video over it, but this is going to be 8 feet per second squared over 2. I'm going to just leave out the units here and put a little NCU here for note consistent units, equals. Now the g times r is 32 times 20, and I believe that comes out to be 1280 cosine theta, where the theta is 45 degrees. I should just put cosine 45 there, I guess, plus the constant. If we solve this for c, I got minus 841 out of that. So our equation here now relating v to theta looks something like this. I'm going to write it on the left here. So now we got v squared over 2 is going to equal 1280 cosine theta minus 841. And I put a couple values of theta in here. I ran it at theta equals 0, theta equals 15, and theta equals 45 degrees. Keeping in mind that the theta equals 45 degrees should correlate with the initial conditions of our problem. And when I ran the numbers in this, make sure I get this right here, I got about 21 foot per second for theta equals 0, 19.9 feet per second for theta equals 15, and about 8.03 feet per second for theta equals 45. Now the 03 is coming from rounding. There's been a little bit of rounding here and there throughout some of this. To two significant figures, this is 21, 20, and 8. 8 matching up with the initial conditions of the problem. So the rest of this, I'll let you finish. I'm not going to bother with this. But to finish this off, I believe the question asked for the normal force at various locations. Well, we now know the normal here at theta equals 0. I'm sorry, we know the speed here at theta equals 0, so we can come over here now, input that speed right here, solve for the normal. If we want the normal at 15 degrees, we just use 19.9 feet per second here, solve for the normal and so forth. Keep in mind when you put these masses in, I know English units are a little on the funny side, the standard unit for mass in Newton's second law equations is the slug. And there are 32-pound masses in a slug. So when you're given a value like 5 pounds, that 5 pounds could be considered 5 pounds force or 5 pounds mass. There is actually a pound mass in the English system. And to convert it to slugs, the conversion factor has slugs up top, pound mass in the bottom, and there's 32 pound masses in one slug. So just don't forget when you're putting these masses in, they need to be converted to slugs. Here's the conversion factor for that. 32 pound masses per slug. So I hope this video helps. I hope that plus and minus sign thing is much more clear now, and we'll be working on that this semester, so everybody enjoy.